So we have a 3-variable system of equations that we want to solve. We want to solve this algebraically. So I'll go ahead and label my 3 equations, equations 1, 2, and 3, just so I can stay organized in my work. So I want to put two of these equations together and use the elimination method to eliminate a variable. And again, it's up to you which variable you choose to eliminate first. So let's say you choose to eliminate x, and perhaps you want to start with equations 2 and 3. Again, looking at 2 and 3 because I'm thinking, well, I have a 4x and a negative 2x. I already have one negative term. So to eliminate x, I would only have to multiply one of my equations by a constant, rather than having to multiply both equations by a constant. So I have 4x minus 2y plus 6z is equal to 14, and negative 2x plus y minus 3z equals negative 7. So if I choose to eliminate x here, then I need to multiply my bottom equation, both sides, by positive 2. So my top equation remains the same. I haven't manipulated it at all. And the bottom equation is going to become negative 4x plus 2y minus 6z is equal to negative 14. So we go ahead and proceed with our elimination method, and we notice that the x terms are going to subtract out, as are the y's, and interestingly enough, so are the z's. So I would end up with a 0 on the left-hand side of my equation, but then on the right-hand side, 14 minus 14 is also equal to 0. So right now, everything's subtracting out, and it's leaving me with the statement that 0 is equal to 0. So you first ask yourself if this is a true statement or not. And certainly, 0 does equal 0 for all values of x, y, and z. So this tells us that we have an infinite solution case. We know that there are an infinite number of solutions, meaning that the 3 planes in the beginning of the problem, those 3 planes intersect an infinite number of places. So once again, you have to remember, in the infinite solution case, there's actually 2 different ways that the planes can intersect. So one option is if the 3 planes intersect in a line. So if the intersection is a line, we say that the system was linearly dependent. The intersection was a line of the 3 planes. Or the planes could actually coincide. And if the planes coincide, then that means that they are actually all 3 the same plane. Think of it as 3 sheets of paper laying all on a table. They're laying on top of one another, meaning they intersect an infinite number of places. So to figure out which case it is, we have to go back and analyze the original system of equations that we were given. And it's probably easiest to ask yourself if it's the second case. Are these actually the same plane? Because if they are the same plane, then that just means that these original 3 equations are actually equivalent equations. In other words, they would just be multiples of one another. So for example, let's start with this bottom equation just because it has the smallest leading coefficient here for x. I have a negative 2x. So look at equation 1 where you have a 6x. So if they're multiples of one another, then I would need to multiply my third equation here. I'd have to multiply it by negative 3 in order to get a negative 6x for my first term. So look what happens if I multiply the third equation by negative 3. We would end up with negative 6x minus 3y plus 9z is equal to 21. If I multiply my third equation by negative 3. And now, compare that with the top equation. Excuse me, catch my mistake there. That should have been a positive 6x. Now you see that, oh, the top equation is actually the same as the third. In other words, the top equation is just a multiple of the third equation. They're equivalent equations, just in different forms. And then we could do the exact same thing, looking at equations 2 and 3. So again, I have negative 2x for my leading term in the third equation, and my second equation has a 4x. So I would have to multiply my third equation by a negative 2. So if I multiply the third equation by negative 2, I end up with 4x minus 2y plus 6z equals 14. And you'll notice that that's exactly what the second equation is. So the second equation is just a multiple of the third equation. So this tells you that these three equations are actually equivalent. And that means that it is the second case here where the planes all coincide. In other words, they are the same plane. So the way you can say that is you can say that this is coincidentally dependent. So again, the first case, we would say the system is linearly dependent if the intersection is a line, but if the planes coincide, they're all the same plane, then we say it is a coincidentally dependent system. So the way we're going to write our answer then, our answer is going to be every ordered pair that lies on the plane. Excuse me, it's not an ordered pair, it's an ordered triple since it has 3 variables. So every ordered triple, x, y, and z, such that, and now you're just going to give me one of the forms of the plane, meaning one of the 3 original equations. And it doesn't matter which one you choose because they're all equivalent. So I'll go ahead and just choose the very first one. 6x minus 3y plus 9z equals 21. And I'll just copy that right here. Again, you could choose any of the 3 original equations because they're all equivalent. And this means that my intersection of the 3 planes would be any point, x, y, and z, that lies on this plane right here. And there's an infinite number of those points.